Hey everybody, and welcome to another JASP tutorial. In this JASP tutorial, we are going to talk about the power module in JASP that came with a 0.17.2 get to 0.1 hotfix in case you haven't. And in this video, we are going to do the one sample proportion power analysis, okay, which is going to be different from what we did before in the previous set of videos because we're no longer talking about Cohen's d anymore. Nope. This is proportion, so things like binomials and things like that. So let's close up plots here. Let's close up data generation. I talked about those in the overview. Please make sure you check that one out. Let's go ahead and grab our one sample proportion test. All right. So this power analysis module is to determine the sample size that you would need if you were doing a proportion difference thing, like a binomial test or something like that. And you have a one sample, so you're only measuring one group of people and comparing it to a hypothesized proportion or a proportion that exists in the literature. Okay, and this is going to tell you how many people you need because of how Cohen's H here is calculated between two proportions. So that's the effect size. The effect size is Cohen's H. Okay, for binomials or for R values, those kinds of things. Okay, so if you think about it, these are proportions, so they're between 0 and 1. So we're going to switch to one sample proportion. Okay, and here we have the breakdown of it, right? The interesting thing is this has the one sample proportion has the introduction language here, which is pretty interesting. This is not the case for the t-test and the z. And the purpose of power analysis is to evaluate sensitivity of a design and test. You have chosen to calculate the minimum sample size needed to have an experiment sensitive enough to consistently detect the specified hypothetical effect size when using one sample proportion test. That's pretty cool. Little flavor text there for you to give you an idea. So here's the table of note. Okay, so by default, when you choose one of these tests, it's going to go into the sample size. So this is the a priori power analysis. This is what the whole introduction text is all about, right? So hypothesized proportion is what we are thinking the proportion is going to be, and then our comparison is what exists in the world previously, right? So I'm going to change this to 0.5 and see what happens. It can't be equal at a two-sided. I love it. So we're going to change this to 0.6. Okay, it's going to be the same because a one sample proportion is symmetrical, right? So we could change the two. It doesn't matter as long as they are the value that you want them to be apart. You can put either one together, right? You can put that value in there. So it doesn't really matter what your hypothesized proportion is and what your comparison proportion is and what those two things mean. If you've got two proportions, just plug them in there and your n will be the same regardless of what order you put them in. So just be aware of that. You don't necessarily need to have the exact right values in each of these boxes because it is as one sample proportion. So just like a one sample t-test, you are comparing your measured thing to an existing value. But the difference here is that H has to be calculated. So you have to have the two here, which is different than the previous power analyses that you've got. So you definitely want to make sure that you at least know these two things. Okay. So let's say I am planning, so I've got a 50-50 chance is my comparison. That's what I think is going to, that's what the world says is going to happen. But let's say my sample, I think is going to be a 60-40 breakdown. So to figure out how many people I need to be able to determine that with a Cohen's H of 0.201, okay, which is small at a 0.9 power and alpha being 0.05, then we need 260 people. Now, if I change this to 0.8, place your bets in the comment section down below. If n increases or decreases, pause now. Let's see what happens. We need fewer people if we're lowering the power. So the analogy that I like to use is imagine our effect size is a needle and the power that we have changes the size of the haystack. So we're looking for the needle in this haystack. How many people do you need in, let's say, an hour to find the time doesn't matter, to find the needle, okay? With the possibility that fewer people means you may end up not finding that needle in that size haystack. And so if we reduce our power, the ability to find that needle, then we are going to just need fewer people, okay? Because those are the ones that are going to be sifting through the haystack. So, and if we leave alpha as 0.05, because we do that conventionally, then how many fewer people? So even if I went down to 0.5, it's whatever, then we only need 95 people, which is great. So if we reduce our power, then we need fewer people. If we, let me put this back up to 0.8. If we reduce our, or if we hypothesize, if we increase our proportion distance, which is going to increase H, right? So 0.3 is the difference between these two, which increases H. Okay, so it's a larger effect. Then we need even fewer people. But let me change this to 0.51, right? So it's only 0.01 difference. We need 19,620 people because H now is 0.02. That's a really small effect, Really, really small effect. And obviously, the difference between these two is 0.01. So of course you need a lot of people to be able to detect that. This is a massive, massive pile of hay with a tiny small needle somewhere in the middle of it. And that sucks, right? Oh boy. Oh boy. It's like the needle is like moved all around. You like put it in the middle and you're like, it's going to be in the middle. I'm going to find it in the middle. And then somebody comes in and just shuffles the whole haystack around, 19,000 people to find that needle. Yeah. So that's how you do a priori power analysis to find out how your N works here. But what if we've already measured the sample of people and we want to know what our achieved power is? And so I'm not going to, let's change this to 0.6. Let's change this back to 0.6. Okay. And find out how much power we have. Oh boy. It's rough with only 20 people, right? Our power is only 0.147, a difference of 0.1 in our proportions, which is a Cohen's H of 0.2. Our power is only 0.147. Okay, so we're actually going to miss it most definitely. But let's say we increased our, let's say we measured 100 people, right? 5 times as many. Then our power increases to 0.52. So the more people that you add increases power, right? So there's a direct inverse relation, or there is a direct positive relationship between sample size and power, right? The more people you have, the more power that you have. So what if you wanted to calculate the effect size, or that is the difference of the observed proportion in this way? So when you change this, then you end up with a new drop-down menu. You either say that P1 is greater than P0 or P1 is less than P0. And the things that change on this table, okay, are P1, what its actual value is, and Cohen's H, okay? So if we just left everything the same as we had in the previous power calculation, post-hoc power calculation, P0 is 0.6, okay? Then and power is 0.8, type 1 error is 0.05, and sample size is 100. Then what we actually calculated was a P1 value of 0.732, because remember, we're saying that P1 is actually supposed to be greater than P0, and Cohen's H is 0.28. Now, if we switch it the other way, which is what we actually hypothesized in our direction, right, this is actually truer to what we set up. So the previous one doesn't actually make any sense. Then P1 changes to 0.461, and Cohen's H is 0.28. So P1 is actually 0.46 if we measured 100 people. So that's how you can find out what the actual proportion difference was, rather than a comparison proportion that exists out in the ether. And that's how you do the one sample proportion test in the power module in JASP. If you have any questions, comments, suggestions, or other feedback, please leave those in the comments down below. Thank you so much for watching. I'll see you in the next one. Bye.